thanks everybody for attending the Autodesk Advanced Manufacturing Summit. My name is Tim Lankisch. I'm the Director of Engineering at CAE Services. My presentation today is a COVID success story, rapid Moldflow response for ramping up ventilator production. So I'm sure you guys have all seen lots of stories on the news and the paper and trade magazines about ventilator production. This is a little story about how we contributed to that. A little bit about CAE Services first. We were established in 1988. There's a picture of our technology center. We have the most expert certified Moldflow engineers in the world. We're an Autodesk Make partner. We've completed some 24,000 plus projects over the years in our Moldflow consulting business, and there's our website if anybody wants to learn a little bit more about us. Here's a little bit about me. I've been around the block for a while, 27 years at CAE Services. I'm expert certified in Moldflow. I've trained a lot of expert certified engineers to the expert level. I'm a trade magazine contributor and previous Moldflow Summit presenter as well. So here's a little bit about my lockdown experience. I'm sure you guys have had similar experiences yourself, but I have 4 teenage daughters, and being at home with 4 teenage daughters didn't make for the most pleasant experience when it comes to the noise factor. So luckily, being on the ventilator project, I am deemed necessary. So I was able to come into the office, and we have a small office here. We also have a very noisy dog, Willie, there in the middle of the picture. So it's good to get away from the house and the noise while my children were home from school. My wife, unfortunately, had to bear the brunt of that. She was working up in our bedroom. She's not a noisy one herself. But in any case, at the beginning of the lockdown, I thought I'd try to get back in shape a little bit, and I tried running, and 3 strained calf muscles later, I decided 50-year-olds probably shouldn't try to run. And then some of the fun that we did, 2 large jigsaw puzzles. That's a 2,000-piece puzzle there that we worked on, and then multiple house projects. So if you had to put a silver lining on that on this lockdown cloud, then I guess those would be some of those things there. So the COVID problem. You've heard chapter and verse on this over the last 4 or 5 months. Back in March, if you think back to then, there were rapidly changing conditions with the spread of the coronavirus. Nobody really knew how potent it was. We talked about flattening the curve. Everybody was in rush, panic mode. And, especially up in the Northeast and New York, New Jersey area, the potential ventilator shortages in those hotspot areas were becoming a real thing. So we had to bring the power of American manufacturing to bear on that. It's really interesting to read all the articles and so forth about how everybody came together, particularly in the plastics industry. We should really be proud of what we've done with all the PPE equipment and the ventilators and so forth. And really, when the people and their government have a common purpose, these great things really can happen. So, like I said, it's amazing how many of these stories we've seen in the trade magazines. Autodesk's role in the manufacturing world I'm sure, is played out in hundreds, if not thousands, of ways during this crisis. The Make Anything model, from the design tools to the simulation tools to the manufacturing tools, I'm sure have played a huge role across the country as this has been going on. And Moldflow's role in particular, which is what I'm going to talk about today, in the plastics manufacturing world, we'll show you a case study here about how we brought the power of Moldflow to get a rapid response on this ventilator. So, and really, I would argue that Moldflow's role in the plastics industry over the last 30 years, I don't know of much else that has had as great of impact as Moldflow has. So here's the ventilator we worked on. This is from Ventec Life Systems. This unit is called VOCSN, and you'll see why in a minute. But Ventec Life Systems is up in Bothell, Washington. And if you recall, a lot of the beginning stories of the coronavirus were in Washington State. This is really the Cadillac of ventilators. It's not just a ventilator. It's the size of a small suitcase, about 18 pounds, and it's 5 devices in one. It gives people mobility that need these on a daily basis. And it's really kind of a game changer. People who need all these things to go into their system, a ventilator, oxygen, cough, suction, and nebulizer, used to have to carry around multiple units. So all of these things are contained in one unit. And that, like I said, is really a game changer. Up to this point, before coronavirus, we'll call it BC, Ventec was up to about 200 of these units being manufactured per month. And when we're talking about thousands and thousands of ventilators being needed for this crisis, you can imagine what they were up against trying to ramp up their production to a much higher level. So that's where GM comes in. So the GM supply chain, with all the lockdowns and so forth, all of the car manufacturers went on lockdown themselves. So that opened them up to help with this project. They called it Project V for ventilator, and it brought their manufacturing might into play. So the full story, if you want to get it, is on Ventec's website. You could probably get it on GM's website as well, and it's all over the news. Essentially, the government contracted with GM $489 million to purchase thousands and thousands of ventilators. The government invoked the Defense Production Act. The FDA was able to relax some of the usual enforcements on ventilators, the regulations, and they were contracted to produce 15,000 ventilators by the end of June and another 15,000 by the end of August. So GM took their Kokomo, Indiana plant and retooled it, so to speak, to be able to produce these ventilators. And they deployed 1,000 workers to scale up production. Their capacity is 10,000 per month, and they're making it scalable if we get into a situation where more and more ventilators are going to be needed. So just bringing that supply chain in on board, something obviously Ventec was not in a position to do. They didn't have the huge supply chain to make thousands and thousands of parts like GM did. So a great relationship was formed there. And then how did we get involved? We've had a long-standing relationship with GM ourselves. We're expert certified consultants, and anybody that knows anything about General Motors Moldflow standards knows that General Motors expects expert certified consultants to be working on their parts. So we've sat on the GM advisory board for many years. We've worked on hundreds, and I would argue possibly thousands of GM parts over the years. And then our windage expertise is brought to bear. And we'll talk about windage a little bit later in terms of helping correct some warpage issues on one of the parts that we worked on. We worked on several of the parts in this ventilator. There's nearly 800 parts. We worked on a bracket for an oxygen metering valve. It's kind of neat how they just numbered all these parts. Number 265, we worked on part number 156, number 157, part number 285, part number 114. But the one we're going to talk about is the bracket, this oxygen metering valve bracket. So this is an exploded view of the whole VOCSN assembly. And you can see this piece right here is the one we worked on. And here's a blow up view of that. And of course, the part itself here. So a small part, a couple inches in size, but has a very important role in this part. Here's another couple of parts we worked on down here, these oxygen sensors. We worked on the main chassis here, and so we've had our hand on several parts within this assembly. So here's the oxygen metering valve bracket itself. It was originally machined out of PEEK, and then they at some point switched over to injection molding. It's a Victrex PEEK 450 FC30, 10% high strength carbon fiber content, 10% graphite powder, and 10% Teflon all go into this material. So some of the existing issues they were having with this part, perpendicularity was a big one. The boss needed to be perpendicular within 2.5 thousandths vertically. And same with the L shape of that bracket, needed to be within 10 thousandths. And then also some very large sink marks on the top surface was something they also wanted to correct on this. The project timeline is one of the big things on this. It was pretty amazing how this all unraveled. Of course, in late January, we saw the first COVID case in Washington State. Around mid-March, the U.S. government got together with GM. By the end of March, GM was engaging PTI Engineered Plastics in Michigan on this particular part. And then a day later, on April 1st, we got engaged. By the end of day one, we had the first Moldflow results. From some of those results, we realized we probably needed more robust material testing. So the next day that was kicked off, the material testing, and this is pretty phenomenal, was done within 4 days. We were working on the CAD model, and we'll explain all this a bit later, but We're performing windage checks, and we delivered a windage model within a week. That's pretty unheard of in this industry. So again, rapid response in Moldflow allowed us to deliver this windage model within a week. By 4/16, the tooling was completed and the first parts were molded. So pretty awesome delivery times on this. And these are stories that are playing around the country on a lot of different parts that are going into the COVID problem here. So here are the Moldflow results on the existing molding design. So we were handed the mold design, the cooling design, the gating, runners, and so forth. And here's the filling pattern that played out. And one of the things I want to point out is the non-uniform fiber orientation. You can see because of the gate location up on the front edge there, you get some of the fibers aligning front to back, some of them aligning right to left as the flow continued down that vertical wall where the large hole is. So you got fiber orientation, non-uniform kind of playing out across this part. And as you know, non-uniform fiber orientation leads to non-uniform shrinkage. That non-uniform shrinkage leads to warpage. Some of the pressure results. With the old material deck, we were getting around 14,000 PSI. When we got the new material back, it included D3 coefficients, so pressure-dependent viscosity. So a minor change to the pressures, slight increase in the pressure was observed there. And here are the warpage results. So from a side view, you can see with the old material deck, and this is blown up by a factor of 3, by the way. With the old material deck, we were seeing the right trend in warpage, and that was confirmed visually for us when we were early on. But the magnitudes were much higher than what were being observed, and that's partly what prompted us to get the material tested. So when we got the new material back, we saw that the deflections, the warpage was a lot more in line with what was being observed. And here are a couple of overlays with actual results, scanned parts versus Moldflow results. On the left, you see in some of the max deflections were around 14 thousandths. Here, the max deflection really was on the bottom. And come to find out later that we think that the original parts actually had a thinner wall here. So that's partly responsible for this deviation here. But in general, the improved material data went a long way towards getting us very accurate results on the Moldflow analysis. And one of the things I love about Moldflow is the ability to really hone in on what the major cause of warpage is. Now, we had, of course, our suspicions on this, having done thousands and thousands of parts. We had our suspicion that it would be the fiber orientation, but this helped us confirm it. So you can see that if we look at the orientation effects, that we see that bend upward here at that kind of fulcrum point there, and then this front area moving downward was due to the orientation effects. Cooling effects were minimal. Those numbers are very small. Shrinkage effects, the numbers are larger, but that's really just the part getting smaller as we see a gradual change in these colors from top to bottom. So this was a confirmation for us that the orientation effects were the main concern. So that was the first thing we wanted to try to focus in on to see if we could use the fiber orientation to our advantage and see if we could get some of the warpage out. So we went with a new gate location. We suggested putting the gate on the side for 2 reasons. One, to get more uniform fiber orientation pattern across the part. And you can see we achieved that. You see more of the fibers going left to right and very few of them going front to back. So that was one improvement there. The other thing was pressure improvement. So 15,000 PSI was reduced down to 9,500 PSI because we have a much shorter runner now. And I would argue also a more balanced gate location within the part. We also went with a larger gate to help us pack out that thick area that we showed before with the sink marks. So larger gate, thicker, wider, allowed us to pack the part out a little bit better to help with the sink marks. So when we look at the L shape, the warpage improvement, and consider during this whole thing that's our idea is to try to get as much warpage out of this as we possibly can through conventional means. And by conventional means, I mean through gate location changes, or in some cases cooling changes that, cooling wasn't a big player here, but in this case, the gate location was. So just by moving the gate location, we were able to get a couple of thousandths out of the deflection. So that downward deflection on the front edge there was reduced from 9.8 thousandths down to 7. And then the inward deflection of that vertical wall was slightly reduced, not a whole lot. And that's not surprising because the fiber orientation really in the vertical piece didn't change a whole lot. And then if we look at the boss warpage, the max deflection on that boss was forward in the Y direction about 55.1 thousandths. And then by moving the gate location, it actually changed the direction of the tilt to the X direction, and that was about 2.8 thousandths. So an improvement there, but there was still some of that left to take care of. And of course, like I said, we're trying to get rid of the sink, and part of the reason for moving the gate was to get that gate closer to the thicker area to help pack it out. And in the original, with the original gate location, you see the excessive sink there. And then on the same scale, by moving the gate to the side, we were able to significantly reduce that shrinkage value. The sink mark estimate, you can see 0.17 millimeters there was reduced to 0.12. So that was a further indicator that we were on the right track. So we got the shrinkage improved, we got the fiber orientation improved, we got the warpage improved, but we're still not where we wanted to be. And keep in mind, we're only just a couple of days into it here. So the next thought is, well, let's go with windage. What is windage? Some people call it Kentucky windage. And if you think about, shooting at a target 1,000 yards away or 1,000 feet away with a Kentucky long rifle, if the wind's blowing left to right, you want to aim left to hit your target, right? So that's kind of where the term came from for those of you who are not familiar. The term applies in injection molding. So what we're doing is we're biasing the steel in the opposite direction of the expected warpage and getting that warpage to come back to the nominal or target shape. So that's what windage is all about. And that's what you can use when the conventional approach doesn't get you where you want to be. So we did as much as we could with gate location. We're on a fast track here. We needed to get things done. Not much we could do with part design. So we had to go with the windage approach. So first step is to determine how much windage. The temptation is to say, okay, well, if we're going to warp 1 millimeter one direction, well, let's just bias it 1 millimeter in the opposite direction, and we're good to go. Well, that's not always the case. Sometimes that factor might be 90% of that 1 millimeter, or maybe it's a half of that millimeter. It really depends on the shape of the part, depends on the material, depends on the process. So we have to go through an iterative process to find out what that windage factor is. So, and this is another really nice feature in Moldflow, is you have the ability to take your warpage results and morph the part in the opposite direction. Just take the mesh, put it in at a factor of -1, and it'll produce a mesh that is in the opposite direction of the warpage that was predicted in the initial simulation. And that's what I'm showing here is the purple is the nominal shape. You see green is the windage shape. So it expanded it moved it up on that top platform there, and it moved it outward on the vertical wall there. So that's what we would expect because everything was moving in. It's taking it and moving it out. Keep in mind that Moldflow is not going to do any die draw corrections for you. It's just taking the opposite shape of what the predicted warpage was. And if you're a mold maker, these die draw corrections are important. Otherwise, you could get some features that would get into a die lock condition, and that's bad news for everybody. Also consider the fact that when you do this through Moldflow, that all of the variations in shrinkage are factored into this particular move here. Whereas, for a mold maker, you're going to cut steel to really, most of the time, one shrinkage number. So that needs to be considered as well. And then, of course, we're running it with the exact same process conditions as we did previously. So we ran the initial windage, and we did a windage check at a windage factor 1, and you can see everything came out pretty much dead nuts on. Everything, you see all these deflections here, or deviations, I should say, are darn close to 0. So that is confirmation. When I overlay my Moldflow results with the nominal shape of the part and come this close, that tells me I've got the right windage factor. So in this case, the windage factor was indeed 1, which is fine. Most of your parts are probably going to come out that way, but it is something that we have to check. And then the next step After we figure out the windage factor is what shrinkage are we going to use? As I mentioned before, the shrinkage numbers in Moldflow are variable. If you poke around a part and look at the shrinkages, they're going to be, an infinite number of different numbers across the part. So we look at the material supplier's published information, which is good. It's a good guide, but it's not the be all and end all. In this case, the shrinkage in the flow direction was published to be 0.3, so 0.003 expansion factor 1.003. And then a cross flow or cross fiber would be 1.007. Okay. So that wasn't quite matching up with what we were seeing in Moldflow. And keep in mind that we had good Moldflow data now. So we're seeing something in the 6 to 9 range, 6.5 to 9 for these estimated shrinkage values, composite shrinkage values. So we had a lot of discussions with the material supplier. And in fact, a little dig on Moldflow's competition, Moldex. The shrinkages that were being predicted by the Moldex software were something in over 10 to 17, I think it was, if memory serves me correctly. So Moldflow, we felt pretty good about these numbers, but they weren't quite matching up with the Victrex numbers on the published sheet. So after some discussions and looking at Moldflow results, these are the numbers that we ended up with. So in the direction of flow across the part, you see we have a lower shrinkage number, which is what you would expect. Same in the vertical direction, because a lot of those fibers were aligned vertically on that vertical wall. And then our highest shrinkage number was transverse to those fibers in the 1.008 direction, front to back. So that's what we ended up expanding our part by before we went to the morphing phase of making a usable CAD model for tooling. And here's the final morphed part. The nominal is in purple, and the blue is the windage. And one of the tricks in the CAD morphing that we have to do is we have to keep those vertical features in die draw. So that's the trick of the trade there. All these vertical features, the bosses, the holes, you name it. And then after we morph the part, now we have to go back and do yet another windage check. And you can see some of the features now are a little bit off, and they fall usually in the category of those vertical features. So this one was 0.003 off. These sidewalls, we decided not to correct these sidewalls. These were bending inward, and those showed some of the largest deviations. But there were no critical dimensions on those sidewalls. And in order to do that, there was a slide forming the back side of this thing. In order to do that, that would have caused some tooling corrections that would have been a little bit more time consuming and probably more expensive. So we decided not to correct those sidewalls, and that bears out here in these results. So first molded samples on April 16th. Here's some of the CMM results that came from that. The perpendicularity of the L shape was within spec, 10 thousandths. We were seeing 6 pretty much across the board. The perpendicularity of the boss, the spec on that was 2.5 thousandths. From 3 samples, we did see one that was out of spec, and that was likely because of trying to keep vertical features in die draw. So we confirmed that on there. We saw right about what they were getting on that 3rd sample there when we looked at the Moldflow confirmation. So we were happy to see that. Moldflow was predicting it pretty much right on. From these molded samples also, the original excessive sink you see on the left, and then the modified sink improvement on the right there. So we nailed that one pretty well. So after seeing the tower, the boss there leaning, a little bit too much right on the edge of the tolerance levels there, we decided to try to correct that. And here are some different ideas we came up with. So we put this moat in here, and you can see those numbers didn't change things a whole lot. This one has the moat plus 3 ribs down here at the bottom. That actually got it within spec here at 13 or 1.3 thousandths rather, but we wanted to keep trying some other things. This is kind of a ramped up moat with a couple of ribs on it. That was at 1.8. This had another kind of a half moat design. That was at 1.5. But the best design came from trying to core some of the material out of the boss. This is not a sealing surface. There's a spring that goes around this thing. So we were able to carve some of the material out of this. First idea was to carve just material out on one side of the part. And you can see that got us at less than 1,000th deflection from top to bottom. One of the problems we came up with on that is that we didn't catch this. There's a keyhole on the back side of this, and it was causing some non-fill issues in that area. So we had to modify that. And our final design, here's that modification there. And we decided to put that spline around the full perimeter. So we were able to carve material out of the boss. And you can see that from top to bottom, that deflection was very near zero. So this is the design that we ended up with. And here are some of the molded samples, CMM results. So again, the L shape actually improved even more. The perpendicularity of the boss was well within spec. Didn't quite get down to the 0.0003 that we predicted in Moldflow, but we'll take this. So that's our design. What do we learn from this? I think the big takeaway is that rapid Moldflow is possible. Moldflow oftentimes is something, that's an afterthought on things. And by the time people get around to thinking about using Moldflow for something, oftentimes it's too late because they think it's something that takes weeks and weeks and weeks to do. But really, rapid Moldflow is possible. It takes the right people. Experience matters. And obviously, we at CAE Services have been around the block. It takes the right relationships. Ventec with GM, and then GM with PTI, and then GM with us. The right relationships make a difference. And us knowing how GM works in their plastics manufacturing world made a big difference on this. The right software, of course, Moldflow, really is the gold standard when it comes to plastic injection molding simulation. It's really developed and matured into something that we can rely on for something like using Kentucky Windage, to the point where we're creating morphed CAD models within a week to be able to use in a mold design to produce parts this quickly. That would be unheard of, would have been unheard of 10 years ago. Having a common purpose, obviously, the government I mentioned before stepped up and put this whole thing into motion with GM and Ventec. Another takeaway I would say is that windage analysis is here to stay. I mentioned it before, but we've done windage analysis for a long time, but really putting the CAD morphing part into the equation and knowing what to do and how to morph it and how to take care of those vertical features is something, again, that 10 years ago we wouldn't have really thought much of, but it's more and more in demand. We've done dozens and dozens of windage projects ourselves now, and we know what we're doing and we know how to get it out quickly. And then lastly, I again, just a big pat on the back to everybody that has played a role, not just in the plastics industry, but in American manufacturing in general, and what we've done to do something good for the country and have something to be proud of with the whole coronavirus situation. Everybody stepped up. Everybody was able to get on board and get PPE equipment done, get ventilators made, the whole 9 yards. So job well done, America. And with that, well, I guess I'll talk a little bit about what's new at CAE. So we are an Autodesk partner. We're responsible for software sales, training, and mentoring. The training part of it, where our motto is building expert analysts. So as I mentioned, I've brought 15 plus people up to the expert certified level. And so I'm tasked with training myself. We have classroom and online training. Classroom, not so much now, but online training for sure. We have our Ask the Moldflow Experts webinars once a month, so look for dates on our website. We have Moldflow office hours. If you ever just want to talk Moldflow and understand something in depth, you pick the topic, we'll be there to talk about it. And of course, we have our new website with webinar recordings on it, and you can follow us on LinkedIn. So that's a little bit about CAE. And now I guess is time for questions and answers. So if anybody has any questions out there, I'm ready to field those.